Sleep. Pardon me if I sound terrible. I have a bit of a cold, so I will try to be intelligible. So, purpose of this tutorial. Why am I here giving a talk about optical networking at theoretically a routing and switching packet type conference? Well, everything we do on the internet largely revolves around fiber in some way or form. But most of the router jockeys that are out there, the people that are building most IP networks, really don't get that much exposure to it. They might work with it, but they're not optical engineers. So that can lead to a lot of confusion, misconception, errors, all kinds of issues out there. So the purpose of this presentation is really just to kind of touch on all of the major aspects of optical networking. So remember, I omitted all of the math. There's entire disciplines out there that focus on this specific field and with lots of math as to how you actually do large-scale optical planning, operation, theory. The purpose of this tutorial is really, like I said, just to kind of touch on every topic, make sure that people are educated in the general concepts of the space, make you aware of what's out there. But that's the gist of it. So the basics of fiber optic transmission. So what is fiber? Why do we use it? So really, fiber is a waveguide for light. It's just a piece of material that carries light from one end to another. So you put light in one end, comes out the other. It's most commonly made of glass or silica. It could also be plastic. Why do we use fiber in the first place? Well, glass is very low cost. It's very lightweight. It's very flexible. It's very high density. So you can build thousands and thousands of strands of fiber into a few inch cable. It's very, very light. You can install it on poles. You can install it wherever you want. It's very flexible. It doesn't have a lot of the bend radius issues of kind of copper and things like that. And it can carry a tremendous amount of information. So today, the kind of standard for what can we put over a pair of fiber, easy commodity thing you can buy off the shelf, sits at about 76.8 terabits per second on a single pair. You can easily carry many different signals, many different simultaneous signals without overlapping with each other, so you can grow and scale and add customers and do things optically. You can carry a signal many thousands, even tens of thousands of kilometers without regeneration. You might need to amplify it, but you don't need to regenerate it, and I'll talk more about that later. And the technology continues to radically improve. So we can do this 76.8 terabits on fiber that was deployed 25 years ago that was originally meant for 100 meg service. The fiber is that infinitely reusable. And in fact, we've actually come full circle to wanting to work with the old fiber today. So a few things about fiber. So light propagating through vacuum is theoretically the fastest thing that we know of that can move in the universe. And that comes out to about 300,000 kilometers per second. So that's written as C. So if something is going exactly the speed of light, it would be 1C. But when light passes through a material that isn't a perfect vacuum, it actually propagates slower than this. So for example, when light passes through water, it has a refractive index, is the way that you describe it, of 1.33. So light passes through water 1.33 times slower than it would if it was just propagating through vacuum. And when light tries to pass from one medium to another with a different index of refraction, you can get a reflection. So if you ever look underwater and you see a reflection coming down at you because you're seeing the reflection of where it's trying to transition to air, that's what you're seeing. So that's why fiber works. It's a principle called total internal reflection. So there's actually two different types of glass inside this fiber cable with two different indexes of refraction. You have the core, which is where your light stays, and it's surrounded by a different kind of glass called the cladding. That has a higher index of refraction. That's why the light is always being reflected back into the core. So as long as it comes in at a certain angle, then it will continue to bounce off the inside of the fiber, come out the other end. If you come in outside of that angle of acceptance, then it wouldn't do that, but that's the way fiber works. So here's a gratuitous example using a laser pointer, Wikipedia, and a piece of acrylic glass. You can see the behavior there. So Fiber is typically used what's called a duplex system. So the most common deployments you'll see out there, we use 2 strands of fiber, one for a transmit, one for a receive in each different direction. So that's the simplest, cheapest optical system that's out there. But the fiber itself is actually perfectly capable of carrying many different signals in both directions simultaneously. It just requires more expensive optical components to do so. So whenever we deploy a system, we make a decision as to how expensive is this fiber, how constrained is this fiber, is it worth optimizing, is it worth trying to get everything down to 1 strand of fiber, which we could do, or is it sometimes just easiest to use 2 strands of fiber, or can we just throw more pairs and pairs and pairs of fiber at the problem? And a lot of systems will use ribbon cables and things like that to throw more fiber at the problem. So it's purely a function of economics and the cost of the fiber itself. So the most basic distinction you can have in fiber is multimode versus single mode. So what do I mean by that? Multimode fiber is fiber that's designed to work with cheaper light sources. So the fiber itself has a very wide core, and it lets you use these cheaper, less precisely focused, aimed, and calibrated light sources. So in older standards, it would use LEDs. These days, it's using more laser stuff. But the premise is you won't be able to get very long distance over multimode because the core is so wide. It causes what's called modal reflections inside. So you'll only be able to get tens to hundreds of meters of distance, but you'll be able to use these cheaper optics. And interestingly, the cable itself is actually more expensive than single mode, but the optics themselves are a lot cheaper, and that can be a much better, much bigger benefit. So there's a couple different kinds of multimode that are out there. The older stuff that you'll see that has an orange jacket is what's called OM1 or OM2. This is otherwise known as FIDI grade fiber. So this came out around 100 meg FIDI type connectivity, and it's designed for that low speed signal. So we'll either have a 62.5 micron core or a 50 micron core. Really, you see this in the 100 meg and gig type signal. You can do 10 gig at it, but you really start to get very limited distances. And then if you want to do 40 or 100, you pretty much can't do that with this kind of fiber. The newer type of fiber that's out there is called OM3 or OM4. And this is laser optimized. So it's actually interesting. The standard, the closest thing that's a standard out there, the TIA standard, says aqua fiber for both. But a lot of folks have started moving OM4 to this violet kind of purple fiber to indicate that it's a slightly different fiber. But it's fiber that's specifically optimized for modern laser 10 gig, 40 gig, 100 gig type signals. So it has much higher bandwidth capability. For example, on a 10 gig signal, you go from a 26 meter link to 300 to 550 meters. And if you really want to do 400 and 100 gig signal, or 40 and 100 gig signals, you definitely need this kind of fiber. Single mode fiber is used for high bandwidths and long distances. So it has a much smaller core. It's between 8 to 10 microns in size, depending on the exact nature of the fiber. And there's no inherent distance limitations due to modal dispersion. So that means you can keep carrying a signal as long as you amplify it every about 80 kilometers, give or take. You can carry this on for tens of thousands of kilometers if you really want to. But single mode fiber has a really broad array of types. So it also has something like that looks kind of like multimode, where OS1 and OS2, but in single mode that means something different. So OS1 means tightly buffered, like what you would see in an indoor patch cable, and OS2 means it's loose fiber that you would blow through a duct. So it means something very different. You'll also hear something called SMF28. That's one of the most classic fibers on the internet. It's actually a Corning product name. So it's kind of the gold standard. It was like some of the original fiber that was deployed widely going back to the 90s. So, but single mode fiber comes in a lot of different types. It comes in low water peak, dispersion shifted, non-zero dispersion shifted, bend insensitive, and a bunch of others. And I'll talk more about that in detail later. So here's a diagram kind of showing you the difference, so you can see conceptually the size of the fiber and how the wider multimode fiber has more room for the light to actually reflect around and create modal dispersion inside there. But that's the comparison. Here's some examples of different fiber connectors that are out there. So this isn't the talk to go through every type of fiber connector, but just to give you an idea of some of the different ways that you can terminate fiber. Everything from in the things that stab in and lock in place to more modern things like LC, higher density things, MTRJ. MTP cables. There's a wide variety. Typically the blue tips means that it's, I'll talk more about this later, but it means it's a polished connector. The green tips mean it's an angled polished connector. There's a color code. There's a different a scheme to every different fiber connector that's out there so that you know what you're getting and what you're plugging into. So now I'm going to go through a bunch of basic optical terms and concepts just to talk about these just general concepts. So first thing you have to know when you work with an optical network is something called optical power and attenuation. So optical power is just the brightness, the intensity of the light. So if you think about light traveling through fiber, as it's propagating down the fiber, some of that energy is naturally going to be lost. So it's either scattered by microscopic imperfections, so you can have imperfections where it just escapes through the cladding and doesn't continue to be reflected internally. Or sometimes you'll actually hit different hydroxyl molecules and dopants that are in the fiber that will kind of be converted to heat. So you'll lose a little bit of power over time as you propagate through glass. So that loss of attenuation or that loss of intensity is called attenuation. So no matter how good the fiber is, as you propagate across fiber, you're going to lose some light over time. And we measure that in a unit called decibels. So a decibel is 1/10 of a bell. It's a logarithmic scale unit that expresses a relationship between two values. So that's something a lot of people don't understand. Decibel is what's called a dimensionless unit. It doesn't actually describe, it's not like saying 100. It's not an actual unit. It's describing two things. So if you want to, all right, here's an example. -10 decibel is 1/10 the signal. -20 decibel is 1/100th the signal. So you see the logarithmic relationship. Another really easy one, it's not quite as precise, but it's really close, is whenever something goes up 3 dB, you've doubled the signal. When it goes -3 dB, you've cut the signal in half. But remember, it doesn't tell you double of what. It's just that value. So if you want to express an absolute value, if you want to express this level of brightness, you need a reference. And in optical networking, we use something called a dBm. That's a decibel relative to 1 milliwatt of power. So 0 dBm is an absolute measure of brightness that is 1 milliwatt of power. So like I said, +3, you've now doubled that. You're up to 2 milliwatts. If you were at -3, you've cut that in half. You're at 0.5 milliwatts. But confusing these two is probably the single biggest mistake that you'll see in the field. You'll see people go out with light meters and be in the wrong mode and get the wrong value. So be very, very aware of which value you're working with when you look at these. So why do we measure light in decibels? Well, light, just like sound, follows what's called the inverse square law. So that means the distance, the signal is inversely proportional to the distance squared. So here's an easy way to think of that. You send a signal, the signal travels distance x and it loses half of its intensity. So now what happens when the signal travels 2x? Well, it loses half of its intensity again, so only 25% remains. What happens when it travels 3x? So it loses half again, so only 12.5% remains. 4x, it loses half again, so 6.25% remains. If you use a logarithmic scale, it makes the calculations a lot simpler. So imagine, convert that into a 3 dB change. Now you could say that there is 3 dB of loss per distance x, and as you move 2x, 3x, 4x, you see 3 dB, 6 dB, 9 dB. It makes the elementary school math and it makes it easier on the humans to work with. That's the whole point of using a logarithmic scale. Here's a handy little conversion table that you can look at if you ever want to figure this out. You can also just Google dBm to MW. You can find all these wonderful handy tables on the internet. So another major concept when you work with optical is something called dispersion. So dispersion just means to spread out. So you have this signal that in some way is spread out, and at a certain point it becomes indistinguishable. You're not actually able to decode what you were originally trying to say. The two types of dispersion that we care about are chromatic dispersion and polarization mode dispersion. So chromatic dispersion is what happens when different frequencies of light propagate at different speeds through a non-vacuum. So this is actually the reason prisms work. This is the reason rainbows work. You're seeing the light spread out because they're propagating at different speeds depending on the frequency. And eventually you end up, after some amount of distance, where what was two clear pulses of ones and zeros now becomes indistinguishable because it's spread out. So chromatic dispersion is actually one of the biggest limiting factors in everything that we do optically. The faster your symbol rates become, the more this is impactful. The wider your laser line width, the more you care. And the worse the wider your line width, the worse chromatic dispersion affects you. And it affects you at the square of the baud rate. So typically, chromatic dispersion was the inherent limitation for all of our optical technology coming all the way up to 10 gig, and is still a major limitation as you look at things like 25 gig and 100 gig consumed of multiple 25 gig signals. It's still a major limitation. We express chromatic dispersion in what's called picoseconds per nanometer. So that's the unit that you measure this in. The other kind of dispersion is what's called polarization mode dispersion. So this is what happens when one polarization of light arrives later than the other. So think about a fiber being a cylinder. Sometimes the fiber isn't perfectly shaped. Sometimes there's different kinds of stresses as the fiber is bent. As the fiber underwent different stresses as it was manufactured, it wouldn't be exactly perfect. And so you end up with a horizontal polarization of light arriving slightly faster or slightly slower than a vertical polarization. And that's what's called DGD, differential group delay, which we just measure in picoseconds. So these are the two things that you really care about when you're working with fiber. The fiber optic transmission bands, the different frequencies of light that we use, there's a couple different ones. So 850 is one of the most common ones that you see used in short reach applications. So this is most of your multimode fiber runs here. These are all your short reach things. It's high attenuation. It lets you use really cheap, simple, basic lasers or LEDs, but it doesn't go very far. 1310 is what's called O band, which stands for the original band, not very innovative naming. And so this covers 1260 to 1360. So this is a 100 nanometer chunk of spectrum with 1310 kind of sitting there at the center. And historical footnote, you'll see some people say 1300, you'll see some people say 1310. They're all talking about the same thing, but it just depends what different people have used to represent the center of this. This is really used for your intermediate reach. This is your 2 to 10 kilometer type reach applications. You'll see it used for longer. Some people are doing 30, 40 kilometers with 1310, but it's the point of lowest dispersion for classic single mode, but it's also a point of higher attenuation. So that's why you see it used for that intermediate reach. The 1550 band, which is called the C band for conventional, is defined around what you can amplify with an EDFEH. And I'll talk more about this in a minute, but it's a big chunk of spectrum that is used for long haul, DWDM, everything that we do that's fancy. It's the point of lowest attenuation. So it's where you can send the signal the furthest. It's where you'll actually be able to get a good 80 kilometer reach or more on an individual link before you have to amplify. This is where you see pretty much everything centered around long reach and DWDM. The only time you see anything different is if you see something using L-band. So L-band is, think of it like an extension to C-band. It has very, very similar properties. It's just an expansion of it. So if you ever fill up your C-band and you really, really, really need to put more capacity on that, they have different amplifiers that will work, that will affect things in the L-band. They have different things that are, all the components have to be tuned slightly to be compatible with it, but it behaves very much like an overlap of C-band with slightly worse performance. Here's what that looks like on a chart. So you see here the dashed line at the top shows the way the fiber worked kind of going back to the early 80s. There were certain peaks. This is called water peak. So basically in the manufacturing process, there are these hydroxyl molecules that get in the glass that are very difficult to take out. And so the early fiber had certain frequencies of light that had very, very high attenuation. You just weren't able to use those chunks. And we used the windows around those water peaks to work with what we put on the fiber. And as you see, the fiber's gotten better and better and better. And these days, modern fiber has very low peak. You still might not want to use the water peak because it's not the optimal point of the fiber, but we've gotten much, much, much better in modern fiber, and we can work with this if we need to, if we're ever spectrum constrained. A big concept in working with optical is something called the OSNR, the optical signal to noise ratio. So if you do any kind of a long haul system, an amplified system, anything that's more than a point-to-point system, the OSNR becomes the biggest thing that you care about. And it's the ratio between the signal, the nice clean signal that we have in the center here of the laser we're trying to transmit, and whatever our noise floor is, whatever that background is that we can't distinguish from our original signal. So this becomes a thing that you talk about later, the performance of optical systems. So now I'm going to talk about wave division multiplexing. So wave division multiplexing, we know that light comes in many different colors. So what we perceive as white light is really just a mix of all of the colors of light. So what that means is that you can have different colors of light combined on the same fiber, and the goal is the light, different channels, different frequencies of light will go right past each other without interfering. So you can have large amount of capacity built into the system by adding more and more and more channels as individual wavelengths, and then you filter it out on the other side, pick just the frequency that you want. That's the general concept of WDM. So there's a couple different ways that you can do that. The most basic way is something called CWDM, which stands for coarse wave division multiplexing. And that's loosely used to mean anything that's not DWDM. It means a lot of different things to a lot of different people. So one popular name is there's 8 channels with 20 nanometer spacing, so like a 1470, a 1490, a 1510. That's a really common thing that's been running around the industry for a while. If you use low water peak fiber, it actually adds another 10 channels, so you can have 18 total CWDM channels that you can work with. It can also be used to refer to something like a 1310, 1550 mux, where you just take these two really simple common frequencies, put them together, and call that CWDM. Or as friends of mine have called it, GWDM, ghetto WDM. Dense wave division multiplexing is a lot more standards-based. So there's an ITU grid that defines the exact channels, the exact frequencies. So within C-band, there's a couple different channel sizes that are common. So you have 200 gigahertz, which would give you a 1.6 nanometer spacing. So there's going to be 20 to 24 channels. 100 gigahertz, which is still pretty common, 40 to 48 channels, all the way down to 50 and 25. So the reason for this, this has evolved throughout the year. So 200 gig is pretty uncommon these days. You have to go out to like the obscurest parts of the internet to still find this. This is kind of 2000 era, very old, very antiquated technology. 100 gigahertz is still very common for DWDM in the metro. So lots and lots of systems use 100 gig tunable. Gives you, so when I say 40 to 48 channels, 48 is what actually fits into C-band. And what ends up happening is either you can't fit 48 connectors into a 1U, so people just shave it down to 40 because that's all that fits. Or they'll leave off a couple of bands because they'll also sell products where they'll say, here's an 8, an 8, an 8, and an 8, and they'll leave a channel empty in the middle so that you can stack those multiple 8s. So that's why if you really wanted to push it, you could go all the way to 48, but a lot of products that you see out there are built around something like 40. The 50 gigahertz systems are still the most common, widely deployed commercial long haul. So if you any kind of a long haul system, any kind of an external transponder, any kind of you go to an Infinera or a Sienna, those are the systems that are still the widest deployed and still going in today. 25 actually was used briefly as we were moving our way through technology. We were getting denser and denser and denser. We got all the way up to a 25 gigahertz for 160 or 192 10 gig channels, and then we actually started backing away from that. So 25 is kind of considered old, defunct technology now too, because we ended up finding different ways to pack our channels. But the modern systems can actually be very flexible. There's a technology called FlexGrid that I'll talk more about, where you can actually create channel sizes that are different widths. A lot of new technology actually depends on different widths out there. So you'll start to see a lot of things going forward. You're not going to see these old, it's just 100 gigahertz, it's just 50 gigahertz. You're going to see more advanced things. So here's a little diagram showing a channel size comparison here, just to put it in perspective what a CWDM channel looks like with 4 or 8 or 16 of these versus 80 channels in a 50 gigahertz system in C-band, and what another 80 would look like in L-band. So you see the DWDM channels are much tighter and smaller. So what are the advantages to this? Why do we have these two different systems? Well, CWDM, it's not that the laser is actually any narrower. It's not that the signal itself is wider or narrower. The width of the signal is actually proportional to the baud rate. So as we move like from 1 gig to 10 gig to 40 gig, that increases the width, what's called the line width of the laser, but whether it's a DWDM or not actually doesn't make the signal any wider. The reason that it's a wide channel is because we get to use cheaper cooling systems. So as the laser heats up, it'll move this way. As it cools down, it'll move this way. And because we have this very wide channel, it really doesn't matter where it falls. It still fits in there. The DWDM systems are just more expensive from a cooling perspective. You can have far more channels on a DWDM system. So like I said, you can go up to 96 channels in 50 gigahertz in 32 nanometers of spectrum versus 8 channels at 160. So you can obviously have a lot more capacity. But the big advantage to DWDM is that you can stay completely inside the C-band or the L-band if you wanted. And that's the area where you can do amplification. So I'm going to talk a lot more about that later, but that's the area where you can carry a fiber signal for more than one hop, make it brighter through amplification, and do long haul systems. So other ways that we use WDM, like I said, there's other forms. So the 1310, 1550, that's a really simple, basic, easy way to, hey, I just want to double the capacity of a system. You'll see a lot of multi-lane gray optics. So the way this works is as we move through new technology, as we move from 10 to 40 to 100 to now 400, whenever we create a new technology, it's actually very hard to do a single serial channel. So when 10 gig first came out, it was incredibly difficult to do a native 10 gig signal. So we actually created an early version of 10 gig called LX4, and all it did was run 4 different 2.5 gig waves inside. And it was much cheaper and easier, and it went further, and it was just much easier to work with to use 4 parallel versions of the lower speed signal than it was one high speed version. And then over time, we got better and better and better, and eventually it flips. Eventually it goes the opposite, where the overhead of putting in a gearbox to do 4 lanes becomes more expensive, more difficult than just working with one native 10 gig signal. And so these days you rarely see anything like that, but if you go back 10 years ago, LR4 or LX4 LR4 was a popular standard. So very similar thing at 40 gig. 40 gig E actually doesn't, 40 gig as a native signal doesn't really exist. So if you ever go up to a router and see a 40 gig port, you are never, ever, 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 ever looking at a native 40 gig signal. You're looking at 4 parallel 10 gig signals. And so that'll just run at a CWDM type frequency. Similar at 100 gig. The most pervasive 100 gig standard right now, actually, ironically, LR4 is not the most pervasive. It's actually only like 8% of the market. But from a router perspective, the ones that we see as network operators building the internet, LR4 is the most pervasive standard, is actually 4 different lanes of 25 gig. Because that's much, much cheaper and easier than FR1, which is the single lambda version of it, and will probably continue to be so for another 18 months, 24 months, something along those lines. But 3 years from now, eventually we're gonna cross a point where all of our LR4 goes away and we move to a single 100 gig lambda. You'll also see single strand optics, so BX, bidirectional. So you'll have an optic that just kind of has a little tiny integrated mux in it. So you can if you have a fiber pair, you could use one strand for one link and one strand for another link, and it's just without requiring any specialized knowledge whatsoever. It's just a cheap, easy way to double capacity, and you'll see this used as WDM. So some of the WDM channel terminology. When you hear someone say 100 gigahertz mux. What they're talking about there is the channel spacing. So it's 100 gigahertz is the space from the center of one channel to the center of another channel. But that's describing one very small piece of the mux, right? There's a lot of other things that you care about. So you care about the channel passband. That's the amount of signal that's actually able to be carried across this channel. And if you have a very narrow channel passband, then you clip the light on the edges. So you would get only a small channel in the center. You have ripple, which is the shape of the curve. Sometimes you'll have different parts of the curve that have higher or lower attenuation than others. You have channel isolation, so you care about how effective am I at cutting off the frequency from one side to the other. And so you have adjacent channel isolation, total channel isolation, like how effective am I at cutting off the background noise from other channels. There's all these different things that come into play when you look at DWDM channels. So now I'm going to talk a little bit about WDM networking components in general. So I just talked about it a little bit, but a mux and a demux. So this is probably the single simplest, easiest, most basic thing that you'll see in a WDM system. It is a passive, unpowered, generally uncooled device that combines or splits multiple colors of light into a single common fiber or fiber pair. So it's short for a multiplexer. Sometimes you'll hear it called a filter or a prism. So a filter does a better job of describing how it actually works. You're actually filtering specific frequencies of light. But a lot of people kind of conceptually understand that a prism is a thing that splits light, and so you'll hear it called a prism. And a complete system requires a mux and a demux. So generally speaking, you'll have, so if you ever crack open like a 1U box, it'll have something like this inside. It'll have the actual mux component, and there'll probably be 2 of them for a mux and a demux, and they'll all be put into one little unit. And this takes, this one's probably like a 16-channel system and combines it into one. Another major component is what's called an OADM, an optical add-drop multiplexer. So if you think of a mux as the endpoint, you think of it as the starting point of a piece of fiber where you take a lot of signals, combine them into one strand, and send it down. An OADM becomes a good midpoint. So it's a way for you to selectively add certain channels without having to drop all of them. So you could do this if you had like 3 segments. You could have a full mux demux, a full mux demux, a full mux demux. But there's a lot of insertion loss. There's a lot of penalty overhead, cabling overhead associated with that breakout of all 40 or 80 of those channels if all you want to do is pass some of them through. So an OADM is just wired so that some of the channels are dropped and can be broken out and some are passed through. And if you build a well-constructed OADM ring, you can reuse different pieces of the frequency at different parts of the ring. So you can have a group of channels that are reused every single time. You can have other channels that pass all the way through. And an OADM is also a completely unpowered passive device. It's very similar in concept to how a MUX works. There's a bunch of different technologies that are used in these passive components. So there's three main types. One is called an FBG, a fiber Bragg grating. So what's happening here is you're basically etching the core of the fiber. You're creating these little tiny notches, and they do this with this very powerful laser that creates these little notches inside the fiber. And the exact distance the notches are creates reflections of certain frequencies. So you etch a tiny little piece of fiber, and it creates okay, we will reflect this little 10 nanometer chunk back. So here you see this little diagram. There's a chunk here that as the light comes in, this one frequency is reflected and everything else is transmitted through. And then you stack multiples of those on top of each other to create your system. So these are very common in low channel count systems, kind of your 8 or less. If you just have a basic 1310, 1550 or any kind of a thing like that, these tend to be FBG based. The medium channel systems are what's called thin film filter. So it's a lot of the same technology used in photography. You're creating these optical filters with different colors of light, and so you pass through and you filter out different ones. The more interesting one, the one that you see for the larger systems, is what's called an AWG, an arrayed waveguide grating. So if you've got a 40 channel system, that's definitely what this is. If you've got an 80 channel system, typically it's just two of these glued together. What this is two prisms. So imagine you have an input and output, and you have a prism on one side that spreads the light out, and it spreads it out into a big array of fibers. So if you've got a 40 channel system, there's 40 fibers, and they're all a known length. So this one strand is slightly longer than this strand, is slightly longer than this strand. So it comes together into another prism, and because of the different lengths of cable, you're creating a giant interferometer. You create a lot of constructive and destructive interference. And so it ends up breaking out these signals into your 40 or 80 different channels through constructive and destructive interference. But that's how it works. The original versions required active cooling. The ones you see these days are what's called an AAWG, athermal. So they're basic standalone. They require nothing. And that's what you'll see in most of those systems. So another thing you'll deal with is what's called a reconfigurable OADM, or a Rotom. So a Rotom is a software reconfigurable OADM, and it's built around a piece of technology called a WSS, a wavelength selectable switch. So your common architectures, one way to do it is what's called broadcast and select. So one side is just a passive splitter. So if you have potentially 4 different ways that you want to steer a wave, you might just take the light and split it 4 different ways, and then select on the other side. The other method is called route and select. So you actually deliberately, I steer a wavelength this way, and then I steer a wavelength as I receive it. These require a lot of amplification, but it lets you build, I'll talk more about this in a second, but lets you build more complex, more interesting architectures. When you think of a Rotom, the most important thing you think of is what's called the degree, the different directions that light can be steered. So here's an example of what would be a 4-degree Rotom. You have a north, a south, an east, and a west that you could potentially steer the traffic, plus a local add drop. So you can, in this node, I can inject traffic and I can steer it one of these different directions. So I could create new light and send it out link 1 or link 2 or link 3, but I can also say I want channel 31 from direction 1 to go to direction 3. I can stitch these together. And if you actually look at kind of how it's constructed internally, it's just these WSSs, these wavelength selectable switches with a big array, with a big old grid of one connected to every other possible degree. And so you're deliberately steering, all right, I want to steer this wavelength towards this direction. I want to steer this wavelength towards this direction. The more and more you do this, the larger this becomes, until eventually you have this massive pile of fiber interconnecting all these things. So if you think about a fixed OADM, or otherwise called a FOTM, or just a classic OADM, you can create these optical connections between nodes at any point. So you could build a ring like this. You could just run fiber in a ring, and you could arbitrarily say, I want to connect node 1 to node 7, but it's static. This has to be created when you design the original channel plan and the device that goes in. If you ever want to change that, you have to go out and swap your hardware, so it can be time consuming. It requires a lot of man hours to plan and support. So if you really want to figure out your optimal channel plan, you have to put some time and effort into figuring that out beforehand. But it's really cheap. It's really simple components. It's really cheap. It's very little effort goes into it. There's very little loss to the whole system. A Rotom lets you dynamically connect to any point. So once you deploy a Rotom, you have complete flexibility. You can build any optical topology you want. You can connect any point to any point optically. You can do it all in software. You just log into a device, and people build GUIs around this, so you don't need any specialized knowledge whatsoever. But it's all built on very expensive, very complex pieces of equipment, both in terms of cost and in terms of optical performance. So there's different kinds of Rotoms. So the evolution of the Rotom, if you follow it from the most basic, it started out as reconfigurable. So you could change the channel that you wanted to add or drop or pass through, but all it did was go, like once you made the decision to go here, then it would just go to a standard mux to be broken out. So a specific frequency would still be connected to a specific port. So if you had channel 41, it went to a port that was labeled channel 41, and you plugged a cable into that, and you ran it into something that said channel 41 on your optic on your router. And if you ever wanted to reconfigure anything, you had to go send a tech out to recable. So then they created what's called a colorless Rotom. So that eliminated the need to map a specific frequency. Basically, it's just a big multicast array. It's you send the signal out every different channel, and you let the other side select what it wants to receive. So now I can do things like, I'm using channel 41 today, but I can change it to channel 42 tomorrow, and all I have to do is log into a device and type that and enter, and it does it. The latest generation of Rotom is what's called a CDC, a colorless, directionless, contentionless. So colorless, we already said, means that you're not mapping a specific channel to a specific port. Directionless means that you can send the channel any direction you want. So you could send it in this way, east, west, or north, or not. And contentionless means that there's no internal contention. I can reuse that same channel multiple different directions. So obviously I can't reuse, if I have channel 41, I can't send two different channel 41s east, but I could send one east, one west, one north, and none of them would conflict with each other. So what's the goal here? What's the whole point of doing a CDC Rotom? Well, the goal is to make this able to work entirely in software. So you can reconfigure these transponders onto different paths. You could reallocate them. So for example, time of day traffic. You might have an off-peak and an on-peak where at midnight, you might have a lot of traffic going to Asia, and you might have very little traffic being delivered locally. And as that time shifts, you might now be sending a lot more traffic to Europe, and you might be sending a lot less to Asia. So you could potentially remap where these individual transponders are used without having to buy two of them, without having to buy that extra capacity. It lets you go out and do this dynamically in real time based on changing conditions. So there is a lot of standardized work going on in the IETF. There's something called PCEP, the Path Computation Element Protocol, where you can have your network tell your optical layer, I need this amount of capacity. It looks like I'm sending this much. Please reserve me this amount of capacity. And the optical layer will go out and map, dynamically move around and reserve that capacity. And on the one hand, there's a lot of great potential for reuse of transponders and making them more efficient. And on the other hand, it makes the transponders less efficient when they do that in general. So what I mean by that, let's take a look at what actually goes inside of a modern CDC Rotom. It's a little piece of black magic that's happening here. So the very first thing you do when you come into a Rotom, you have to amplify, because a Rotom is about to destroy your signal. So you have to make it really, really bright. Then you come in through a very large WSS, so let's say like a 1x20. So you have 20 different possible ways that you can steer a thing. So that is going to cause a ton of insertion loss. So as soon as you come out of that WSS, you're going to need to amplify again. And then you're going to go into what's called a multicast array. So this is an example of like an 8x16. So you have these arrays of amps that take these many different, because like this 1x20, you have 20 different possible degrees, 20 different possible paths on the back end. Well, every one of these needs an amp. Then it's going to come into this thing that takes the signal and amplifies it out of a very large number of ports and then splits it. And then on the receiver side, you plug into a port and you say, oh, I want to tune into channel 21. I want to tune into channel 22. There's a lot of complexity that goes on in this, both in terms of absolute dollars and in terms of what it does to your OSNR, what it does to your signal quality, what you're actually able to get out of the system because of everything that you put in here. So you're trying to strike a balance. Do you want that flexibility, or do you want to optimize for performance and cost per bit? You have a concept called DWDM super channels. So what's happening here is, imagine what happens if you want performance that you can't actually get out of a single carrier. So here's a simple example. Say someone came to you and said, I need 1 terabit Ethernet. How do I do this? We don't have a technology off the shelf that does that in a single carrier. We just don't, right? It would be this massive 320 gigabaud, 375 gigahertz wide. We don't have it. It doesn't exist. You could do it in 2 different carriers. You could do it as 2 different 160 gigabaud systems, or you could do it as 10 different carriers. So something that we absolutely have off the shelf that's been around for many years is 10 by 100. But what'll happen is you'll take those 10 different 100 gig carriers and you'll cram them together into a super channel. So sometimes you can just get more efficient about the channel packing, or you can just think of it logically as a single. You never had the ability to pull a single one of those out. It only behaved as though it was one larger channel, but it's actually a super channel of many different subcarriers inside that operate at a level that we actually have the technology to do. There's been a lot of evolution through the years on that. So the way that it used to work is we had these different shaped signals and different line width signals depending on the baud rate that we were sending at, and we would kind of cram them into here's a 50 gigahertz grid, whether you want it or not, and it doesn't really matter how much your channel consumes. It's going to fit in here. It's going to be lumpy. And the more modern evolution is that these different signals, you can actually have a system called FlexGrid that adapts to it. So you can dynamically tune your channels to the actual carrier that you need to pass. So you can be more efficient in packing your bandwidth. You can do newer optical technologies that are able to do more with higher baud rates, and I'll talk more about that later, but there's a lot of advantages to that. There's a lot of disadvantages because primarily the only way that you access a FlexGrid is through a very complex Rotom. So you have to strike a balance as to whether you really care about that spectral efficiency or not. So some more optical networking components. DCM, dispersion, you'll hear this said as either DCU or DCM, so either dispersion compensating units or dispersion compensating modules. Both are used interchangeably, and I use them both interchangeably all the time. So basically it's originally started out as a big spool of fiber in a box. And it was designed to cause dispersion that was the opposite direction, the opposite slope of the transmission fiber. So imagine you run through 80 kilometers of fiber out in the field, you get to the end, and then you run through a spool of fiber that's designed to cause dispersion the opposite direction. It's designed to squish the signal back together. And by the end of it, you come out and hope that you're pretty close to what the signal was originally before you put it in there. That's effective. The original designs built around this dispersion compensating fiber added about 20% to the fiber distance because you have these big spools. So that caused latency. And the newer designs were based on FPGs. So you actually had a small fiber Bragg grating that created the same effect that had lower latency. But this had to be specifically mapped to your channel plan. It doesn't align well with channels. So you actually still see both systems that are out there depending on what you're actually trying to accomplish. There's a component out there called an optical switch. So basically this is just a way to steer light at a purely optical level without having to go from optical to electrical to optical. You're able to steer light. So one way to do this is with what's called 3D MEMS, these tiny microscopic mirrors that are electrostatically controlled, and you can aim the mirrors. You can say aim this way, aim this way, aim this way, and you're able to steer the light from port 1 to port 2 to port 3. So these things are very popular in automated cross-connect systems. So people who don't want to go out there and run structured cabling and go plug a cable in, they can just do this remotely through software. And they're also commonly used in lab scenarios. So if you reconfigure things on a regular basis, it's a lot easier to do it in software than it is to go send a tech out there to move cables around. A WSS I talked about earlier, a wavelength selectable switch, is the component that lets you route an individual wavelength. So the first generation ones were built on these 3D MEMS technologies. The newest ones are actually built on what's called LCOS, liquid crystal on silicon. So it kind of functions similar to, remember the old projector TVs that we used to have before we had flat screens everywhere? It's a very similar kind of a concept. There's a lot of advanced engineering that goes into breaking these things out and having these LCOS filters that can filter specific frequencies and then send it in the direction that you want to go. That's why these tend to be these very expensive, very advanced components. A circulator is something that you generally don't see as an end user, but it's often a part of these internal components. The way a circulator works is light comes in port 1, it goes out port 2, light comes in port 2, it goes out port 3. So if something is reflected, it'll go out one port, and if something is not reflected, it'll pass through another port. So here's an example of how you make an OADM using an FPG and a circulator. You etch an FPG, you create this piece of fiber that has these small etchings in it that will reflect a certain frequency of light. And by using the two circulators on either end, if it's the frequency you care about, then it's reflected and it's dropped or added so you can have a local breakout. And if it's not, then it's passed through harmlessly and continues from one fiber to the other. An optical splitter does exactly what it sounds like it does. It splits a signal. So some of the most common examples, you've got a 50-50 splitter. So you'll often see this used in your really simple basic optical protection. For example, here's two fibers. I want to take this signal and send it down both of them. Put a 50-50 splitter in front of it. You send the exact same light, both different directions. And you have a small optical switch on the other side that's generally just looking at power. So it says whichever one has the brightest signal I'm going to use, and if I suddenly see the signal go away, then I switch to the other one. So it's a really, really easy, cheap way to protect a whole bunch. Potentially, I mean, this could be 76.8 terabits of capacity that you're protecting with a single device to send two different fiber routes. You also see a 99.1 or 98.2 or 95.5, depending on the exact specifics, but it's a very small splitter you'll see used for what's called OPM, optical performance monitoring. So what happens here is you split off a very small percentage of signal and you send it to a spectrum analyzer. So now you can look at it remotely and you can actually say, what's actually going across this fiber? Is my OSNR good? Are my channels good? Are my power level good? You're able to look at the whole thing from a sample point where you have a small splitter. And a lot of muxes and things like that and amps will have these little monitor ports built in. You also have a 1x-n splitter. So this is used in like multi-point distribution. So for example, cable TV. What you'll have is like a 32x splitter. So you take the same signal of light, you amplify it so it's really bright, and then you split it 32 times and you send it to different distribution points because you're sending the same signal to many different places. So optical amplification, this is its whole giant topic about this. So amplification is how you increase the intensity of a signal in a purely optical fashion You're not regenerating the signal. There's no electrical components that care about ones and zeros. You never decode the signal. You just make it brighter. There's different types of amplifiers that do this, and there are different names for the designs depending on where they're at in the system. So the three most common types for where they're at in the system are the booster, the preamp, and the inline. So the booster does what it sounds like. It makes a bright signal brighter. So it's generally used when you're trying to transmit and you want to make this as bright as you possibly can before you send it out so you get the best performance. Preamp is used to kind of precondition the signal before you receive it. So it takes a weak signal and makes it brighter. It's optimized for low input powers and to do this with minimal noise. So you use that at the end. And an inline amp is something that kind of strikes a balance between the two. So you might use that if you're not breaking out a signal, you're just passing through. Here's an 80 kilometer span going to another 80 kilometer span. You might use an inline amp that's striking the balance of the two. So two different kinds of amplifiers out there. The most common one, the most pervasive by far, is what's called the EDFEH, the erbium doped fiber amplifier. So the way this works, you have a small piece of fiber. It's generally like 1 meter, 2 meters, and it's doped. So in the creation of the fiber itself, there's 1 part per million of erbium ions that are in here. And you inject another laser into it. So you come along with a specific frequency of laser. So for EDFEH, it happens to be 980 and 1480. And you inject this pump laser into the doped fiber. What happens is the pump laser comes along and it hits these erbium ions and it bumps the electron into an elevated state. So you move up to a higher energy state. And then when the C-band frequency, when the signal that you're actually trying to transmit, when one of those photons comes along and hits that excited erbium ion, it causes it to emit a clone of the photon and to drop back down to the lower energy state. So that's all that's happening. The reason for the two different pump lasers is that's a way that you can pump the most amount of power into the system. There's two different states. So one's called the unstable state. So you can pump at 980 and it goes all the way up to the second level, and then it immediately falls back down to the first. If you pump at 1480, you go to the quasi-stable state. But you elevate this electron, a good photon comes along, hits it, emits a clone, you've left with a brighter signal. So why can't we do this forever, right? This sounds genius, this is amazing, why do we need to ever do anything else? Well, if you don't, so when you get to this good state, you have about 10 milliseconds is the magic window of which you have for a good photon to come along. If a good photon does not come along within 10 milliseconds to hit this excited erbium ion, then it will spontaneously decay and emit what's called ASC, amplified spontaneous emission, otherwise known as noise. Once you emit this noise, it's completely indistinguishable from your original signal. There's no way you can ever tell the difference. There's no way you can decode it. Here's an example of a graph showing here's two good, clean signals and how high they are. There's nice laser peaks. But you see that big curve of noise there? That's all junk. That's all stuff that you didn't want in your signal that has no actual signal transmitted in it. And after you do this enough, eventually you become completely indistinguishable again. So this diagram, what I'm trying to show is one of the things that people don't understand is the input power directly relates to how well your output power will be. So in this example, if I were to let the signal go 5 dB before I amplify it, so that's this top blue line. If I was to let the signal go 5 dB, amplify it, and then go 5 dB again, and then amplify it, and then 5 dB again, and amplify it, and I did that 10 hops, I would finish those 10 hops almost the exact same OSNR. So if I started with a 24 dB OSNR, I'd be at like 23.9. The lower you let the input signal get before you amplify it, the higher a proportion of time there is, the greater the chance that those 10 milliseconds expire. the good photon doesn't come in, and you emit noise. So the lower you let it get, the weaker, the less you're able to continue this. So in an ideal world, you'd be able to amplify constantly. You'd be able to amplify every 10 kilometers. Problem being that's really expensive and really difficult to do. So we try to strike a balance. We try to amplify enough to not let the signal be degraded, but you could let it go to 120 kilometers, but even though you amplify the signal and even though it comes out bright, because you let it get so low first, you've added a lot of noise to the system. The other kind of amplification besides EDFEH is called Raman. So Raman amplification works on a principle called stimulated Raman scattering. It's actually a bad thing when it happens unintentionally, but if you use it intentionally, it's a good thing. And the way this works is you actually use the fiber itself. You use the transmission fiber itself as the gain medium. So in an EDFEH, it's what's called a lump design, right? You have this little tiny spool of fiber, and you come in, and after you leave this spool of fiber, the signal is brighter. In a Raman system, you actually put a pump laser onto the transmission fiber, and it makes the signal brighter as it's propagating. As it's coming to you, it gets brighter. And the best way to do Raman, because of this effect, is what's called counter-propagating. So you actually send it backwards. So if the good signal is coming this way, you send your Raman pump this way. So here's what this looks like from a function of energy transfer. So you have your probe, your good signal coming this way, and you have your Raman pump laser going this way. And SRS, the stimulated Raman scattering, is actually a power transfer. You drain the power from one frequency and you transfer the power to another frequency. So at the end of this, you have a depleted pump going one way, which is filtered out later, and you have your brighter signal that you actually care about going the other way. The reason that matters, so if you look at EDFEH-only amplification, it's very linear, right? So you start out and as you amplify, you make the signal brighter, and then it goes and it loses power over time, and then at a certain point you amplify again and it gets brighter. But the two things you care about are the high end and the low end. When you make a signal too bright, you create something called nonlinear effects. And I'll talk a lot more about that in a second, but you don't want it to be too bright. There's a certain amount of power that you can put into the system, and eventually you hit that limit and it causes all these issues. And like I said before, you don't want it to be too weak either. If you let the signal get too low, then when you amplify, you create all this noise, and you lose your OSNR. You're never able to recover the signal that you put in. If you use EDFEH and Raman together, here's what happens. On the one end, you don't need to transmit as high. Because I've got another form of amplification, I don't need to, so the black line was what I had to do when it was an EDFEH-only system. I had to start out high. I had to start out so high that I went into this nonlinear zone. Now I don't need to. Now I can use an EDFEH, but I can use it at a lower power level, so I stay out of the nonlinear region. And then as the signal comes in, you see the Raman pump, the counter-propagating pump going backwards. You see the signal actually starts to stop getting dimmer and goes brighter. And so as it comes in, I actually start out at a much brighter signal. So now I go into an EDFEH again, but I've done it at a better way. I've done it with a brighter signal, so my EDFEH is more effective, so I'm able to carry that signal a lot further. And the combination of these two is very, very effective, and much more effective than either one used independently. So here's an example of how that works. Let's say, for example, that you had a 21 dB OSNR. This was a target that you had for a particular transponder. When we did it as an EDFEH only, you see the blue curve here, we fell below the 23 dB or the 21 dB OSNR line after 7 hops. So if, for example, we had 100 kilometer hops, we had 7 of them, we went 700 kilometers, and then we lost the signal. So we would not be able, if a customer came and said, I needed an 800 kilometer signal, we wouldn't be able to do it with this kind of a transponder. If you look at the performance gain of using EDFEH and Raman, we take it all the way to 2,000 kilometers. We can go now to 20 hops of the exact same kind of distance and still keep that really high signal quality and still send that signal. So it's a tremendous, tremendous win in terms of performance over distance. When you amplify, you also have to balance the power. So these amplifiers are creating their own unique issues. You don't want a situation where one channel is significantly brighter than the other one. It would cause OSNR issues. If one channel is significantly brighter than the other, then it's going to lower the amplification that happens on that dimmer channel, and it's going to come across and have problems. So what you do to try to compensate for this is the most basic thing is something called a GFF, a gain flattening filter. So it's basically a statically designed attenuation thing that's designed to kind of flatten this out. So it's generally matched to your EDFEH, and it's generally a part of the amplifier itself. So what actually comes out of an EDFEH it might look like this, right? One channel is significantly brighter than the other, but inside of the EDFEH, it has a filter that tries to flatten that out so that all the channels are consistently bright. And a lot of what you do in a complex optical network is make it brighter and then make it dimmer, and then make it brighter again and then make it dimmer. So you play this battle back and forth trying to keep everything balanced. And you can do this with a static map for quite a bit, but eventually you hit a point where you need to do what's called DGE, dynamic gain equalization. So that means you need to have something that actually intelligently, without trying to be statically mapped at manufacturing to the EDFEH, tries to rebalance, all right, this one needs to come 1 dB down, this one needs to go 1 dB higher. Generally that's done with a Rotom. In a complex Rotom network, you'll see often every 7 hops, something like that, 6 or 7 hops, you'll see a Rotom put in just to do channel equalization, even if it doesn't need to steer a frequency. Amplifiers are also limited in their total system power. So you have a limit in what you can put in and what you can take out. So here's an easy way to think about this. Imagine a single channel is 0 dBm, so it's 1 milliwatt of input power. If you have 40 of those channels, it's actually 40 milliwatts of input power, or 16 dBm of input power. So if your amplifier's max input power is -6, and you run all 40 channels, that means you have to, the signal has to be -22 before you can amplify it. And if it gets any brighter than that, you would saturate the amp. So you have to design, if you want high channel count systems, you are automatically forced into low powers, waiting for your EDFEH power to get low before you amplify. The more channels you add to the system, the less power you can have on any individual channel. And so many systems, if you want to optimize, if you really want to optimize for performance, cutting channels out is a great way to do that. If you cut it from 80 channels to 40 channels or 20 channels, every time you do that, you make it double the potential OSNR, double the amount of signal that you could actually transmit per individual channel to a certain point. And this also happens as you change channels. So imagine, for example, you had the power go out in one of your locations. And so suddenly a whole bunch of channels are knocked offline. That directly changes the optical power that's inside the system. So a good EDFEH needs to react to this. So even the basic ones will have a feedback loop and will look for power changes and will control how much they adjust their gain. And the best EDFEHs will actually communicate. They'll have an OSC, they'll have a control channel that talks to the other EDFEHs further down the line to tell each other what they're seeing about the line conditions and to work together to affect the signal. Some more optical networks and concepts, because a few more. Forward error correction. So this is very, very important in everything that we do from how do we actually encode data on the line. So FEC is a way to add extra redundant information so that you can computationally recover from it on the other end. So think of it like RAID 5 for your wave. You add a little bit more signal. So for example, a 10 gig signal, a 10 gig E signal is 10.325 gigabits. Well, if you bump it to 11, if you bump it 7% overhead, you can actually take that same signal and now carry it 120 kilometers instead of 80 and still decode the signal on the other end. So this really matters when you're working with legacy DWDM systems because it's generally not practical to go out and move the amp sites. If you could deploy a system where, great, we could double our capacity, we could cut our cost in half if only I could go move every one of my huts so that they were 70 kilometers apart instead of 80. It doesn't work that way. You've got to work with what you have. So FEC ends up being really critical in making that possible. And there's a couple generations of FEC that we've worked with. So the first gen is something called RS FEC, Reed-Solomon FEC. And it's really simple, really straightforward. This is the one that you see kind of baked into many modern protocols. So like if you do 100 gig SR4, it's built in there using RS FEC. And it's a 6% overhead, and you get about 6 dB of net coding gain of improved OSNR that you were able to work with. You can go 6 dB lower and still decode the signal than you would have if you didn't have FEC. There was a second generation FEC called EDFEH, where they added slightly more overhead and got slightly better performance. The modern FEC actually adds a lot more overhead. So it's something called soft decision FEC. It doesn't actually for sure tell you whether something was a 1 or a 0, but it helps influence the coherent transponder. And I'll talk more about that later, but it informs the DSP what part of the constellation, what it was you were trying to decode. And so it uses a lot more overhead, but it gets you, 1 to 2 dB gain in OSNR can be hundreds of kilometers, right? It can be a massive increase in performance. So this is the modern version is all built around soft decision FEC. And like I said, FEC is key in things like 100 gig SR4 and all kinds of things that we use and think of as client optics actually have FEC built into them or required on the host board as a part of the protocol. So here's kind of an example of how that works, right? So the blue line is what would happen. So it's your bit error rate versus your OSNR. So as your OSNR gets lower and lower and lower as you go to the left, your bit error rate gets higher and higher and higher. If you were to lose, you come down to 10 dB of OSNR, your bit error rate is 10 to the negative 3. That's terrible. You're getting a huge number of the packets have errors, and that wouldn't be a usable signal. But if you have a good modern FEC system on it, you're able to go all the way down to 9 dB before you hit this cliff and you start to lose your signal. Why is this not working? Did my battery die? Nope. It's tired. Oh, okay, come back. All right. So another concept is called OTN. So G.709 or OTN digital wrapper technology. Sorry, snotty. So the way this works. OTN is a modern replacement for SONET and SDH. It's a way to take lower speed signals and mux them together so that you're able to transport them across an optical network. So it works like a wrapper, right? So you imagine you have a 1 gig signal coming in. You might want to run that across you might run 10 1 gig signals across a 10 gig optical carrier. Or a modern version of that might be 10 gig signals or 100 1 gig signals across a single 100 gig optical carrier. OTN is the protocol that lets you individually tell what those things are. So it carries some of that debugging information, right? You can see where the different components are along the way. You can tell what the thing is. So maybe I'm carrying a a GIGI, maybe I'm carrying an old Sonnet signal, maybe I'm carrying frame relay still, maybe someone still has an ATM card that they're running across this. OTN lets you tell what it is and lets you mux many of these different independent signals together in a way that's modern. So think of it as the modern replacement for kind of Sonnet and SDH. Different types of single mode fiber that are out there. So I already said that there's many different kinds, and single mode is used in almost all of your long reach applications. So the basic common standard one that you hear about the most is what's called G.652. So that's standard single mode fiber, otherwise known as SMF28. That's a product name, but you'll hear people call it that. That's just the standard stuff. There's a kind called full spectrum or low water peak fiber. So that's actually modern 652 kind of assumed that. So modern fiber, if you were to just buy regular standard fiber, is low water peak fiber. And it would just be 652D. It would be the latest revision of that standard so that it can work with as many channels as possible. There's a kind called dispersion shifted fiber. There's a kind called cutoff shifted low loss fiber. So that's your submarine cable type systems. A whole bunch of different kinds. So your standard single mode fiber, this is the one that is the widest deployed. It was in all of your original cables. Anything that was out there in early fiber days is still there. And most modern things that go out there are still some variant of this. Like I said, SMF28 as a Corning brand name, but it can be anything. You could also call it NDSF, non-dispersion shifted fiber. So the original SMF that was out there was designed for 1310. That was what it was really optimized for. And that's the point of lowest dispersion. And this is all fiber that was created before the invention of WDM. So remember, wave division multiplexing is a relatively modern invention, right? It's barely 20 some years old. So there was a lot of fiber that was deployed when the premise was just to go out there and run a single channel, and that was all people knew. So ironically, it's actually come full circle to this is now the kind of fiber that we want to deploy on new systems. But for many, many years, we spent creating new kinds of fiber to go out and deploy, thinking that we were solving problems. So like I said, there's the low water peak version. This is the kind that opens up more frequencies. So you get this spectrum over here in E-band that you can use, that you could use with CWDM channels. There's a kind called dispersion shifted fiber. So what happened here was someone got the bright idea, all right, what if we design the fiber so that instead of the lowest dispersion being at 1310, what if we could shift that so that the lowest dispersion was over at 1550, the same point where the lowest attenuation is. So now we're able to carry a signal and keep it bright and hopefully keep it, have less dispersion. So dispersion shifted fiber was that first attempt. And it works well on a single channel system. So if all you ever want to do is put one carrier across a fiber, great. And then they created DWDM, and then they realized, oh crap, this is a real problem. Because what happens when you do this with many different carriers is you create huge nonlinear interactions. The reason for that is you actually want what's called walk-off. You want dispersion helps. Dispersion spreads the signal so that in any given molecule, in any given instant, the power is spread out across many of them. And if there's less dispersion, it's all passing through that one molecule right then, and that's causing your nonlinear effects. So you rarely see this fiber deployed anymore. It was just kind of ripped out and unused and considered a commercial failure. So then they said, all right, let's, what if we did it so that we didn't hit zero dispersion, but we hit just outside. So we shift the point of zero dispersion so that it's just outside the frequencies that we want. So we have lower dispersion, but it's still not completely gone. It's still there. So then you have, to manage that, you have two different kinds of fiber, right? So you have your transmission fiber, which causes dispersion in one way, and then you have your compensation fiber that compresses the signal optically and sends it back the other way. And you switch back and forth between these two slopes, and so at the end of it, you come out with relatively little dispersion compared to what it would have been across this very, very long system. And this is the way that we built long-distance 10 gig networks. It was all kind of predicated around this kind of technology, because you have to dispersion compensate in those types of systems. Another fiber, G654, is the ultra low power, the ultra low attenuation high power cable that you see used in submarine systems. And you'll see G657, which is typically what your patch cables are made of. This is called bend insensitive fiber. So you can go out and flex it or wrap it around your finger or do whatever you want, and it won't cause attenuation. Like I said, perfect for patch cable use, really, really common for that. But if you were running 1,000 kilometers of it in the ground, you wouldn't. There's no point, right? You would want the cheapest, best performance fiber, which is your 652. And modern fibers are better than these specs. So the newer the fiber, generally the better the quality, the better the performance. So here's an example of some of the different dispersion rates of the different commercial fiber types. So you see the value that is typically used to describe chromatic dispersion of SMF28 or standard G652 is 17 picoseconds per nanometer. So you see that's kind of right in the center of C-band, 17 picoseconds per nanometer per kilometer. So if you went 1 kilometer, you would have 17. If you went 2, double that. But you see there's a slope to that, right? So if you're on one end of the C-band, it's a lot lower. If you're on the other end of the C-band, it's a lot higher. So the other slopes here, there's different brands from different manufacturers. There's Leaf, TrueWave, Terralite. There's a lot of other brands out there, and they each have their own slope. And so when you go to dispersion compensate, you have to slope match. You have to make sure that your dispersion compensation is designed to counter the kind of fiber that's actually in the ground that you're using. So nonlinear impairments, I talked about this a little bit earlier, but nonlinear impairments, the best way to describe this is high power problems. So if you don't transmit at high powers, you will never see these problems. People ask, well, how high is high? And the answer is it depends. Generally speaking, you start to see right around +4 dBm per carrier. That's where you're into the nonlinear zones, right? So if you keep your power less than that, which if you just run, even if you run an 80 kilometer DWDM system from your router, you're probably going to launch at like a 0 or a +1. Unless you then immediately go into a booster, you're never going to see a nonlinear problem. You only see this when you're really trying to get as much power as possible through the system. So nonlinear impairments, there's two different kinds, right? So one kind is stimulated scattering. So this is SBS and SRS. And the other kind is called the Kerr effect. And that's what's happening when the light is actually causing the refractive index of the fiber to change in response to the amount of light that's in the system. And that causes some things called four-wave mixing, self-phase modulation, and cross-phase modulation. So the most basic, simple one, stimulated Brillouin scattering. So basically this is when you put so much power into the fiber that it actually causes the molecules of the glass to vibrate at an acoustic level. And when it starts to vibrate, it starts to set up these harmonics, and it actually, in vibrating in a certain way, will cause the power. Eventually, you stop being able to put power into the fiber, and you start getting power reflected back at you. So eventually, this can cause your transmitter to be damaged. This can actually reflect power back at your transmitter and cause problems. And this is very dependent on the power density of the fiber. So the wider the line width, the more you spread that optical power out over wider frequencies. The more dispersion there is on the fiber, the more you spread that power out. You can dither the signal to try and spread that out, but coherent helps quite a bit too. So a modern coherent system does a very good job of spreading that signal out compared to a classic NRZ, and I'll talk more about that later, the classic 10 gig type systems. So SBS impact generally requires a long distance of fiber. So if you run through a 1 meter patch cable, it might not be that big a deal, but if you run through a 20 kilometer span and you're really, really hot, The further you go, the more molecules of glass you move through, the more you have opportunity for that power to be reflected back because of those vibrations. SRS, stimulated Raman scattering, is how Raman amplification works. So what's happening here is you're transferring power from one wavelength to another. Like I said, when you do that intentionally, when you transfer power from a pump laser that you don't care about into a signal that you do care about, it's amplification and it's good. When this happens between two of your signals that you do care about and you don't want it to, it's bad. SRS, the tighter you pack the channels, the more it affects them. So if you have a 80 channel system, the more channels you have, the more it impacts it, but the tighter you pack them, the less it impacts it. So you have this big grid of different performance, right? If you have an 8-channel system with 50 gigahertz spacing, you can go to extreme powers, or you can go to plus 21 per channel and still be fine. But if you run an 80-channel system, you can only launch at plus 0. So if you were to try to come along and launch at plus 3 or plus 4 or plus 5, you'd be seeing significant impact, nonlinear impact from this really strong signal because of the spacing of the channels. 4-wave mixing is an interesting one. So this is what happens when the regularly spaced channels actually interfere with each other and create harmonics. So in this little diagram, you see the orange signal. These are 3 regularly spaced signals. These are the carriers that you're actually trying to transmit data on. And what's happening is because there's so little dispersion on this fiber, the wavelengths are interacting with each other. They're creating harmonics. So you create harmonics to the side on unused bands. Well, we don't care about that because we're not actually using signal. But we also create harmonics on the 3 that we care about, right? We've created a new signal that isn't our data, that just creates noise that's now really hard to decode because of the interaction of these 3 things right next to each other. And if you put them so that they're not evenly spaced, if you spread them apart, if you do other things like that, then you can work around the creation of that effect. But here's why that dispersion, this is what's called mixing efficiency. So this is how badly it mixes. There's 3 different slopes here, right? So the lower one is regular SMF28 with your 17 picosecond per nanometer per kilometer. And so you see a channel spacing, you've got this very, very inefficient, like unless you are incredibly tight, it doesn't want to mix. If you go to no dispersion, if you go all the way to 0, you see that it wants to mix instantly. You're this, like, remember this is a logarithmic scale. So when you're at neg 40 or neg 50, that's not efficient mixing at all. When you're up here closer to 0, that's incredibly efficient mixing. So even having one picosecond per nanometer of dispersion is enough to create some amount of shift, and that's what your dispersion shifted fiber is. Some more diagrams or more examples of different channel counts and different power levels that people can look at. So interchannel effects, these are your Kerr effects. So cross-phase modulation is what happens when one wavelength of light affects the phase of another. So generally, where you care about this is when you're mixing an NRZ and a coherent system. So if you have an old 10 gig system running what's called an NRZ signal, a non-return to 0, and you put a new coherent 100 gig signal on it and they're right next to each other, the old NRZ system will actually cause cross-phase modulation penalties on the coherent system. And the easiest way to prevent this or makes this not cause impact is to have a separation, have a guard band. So if you keep 200 gigahertz of spacing between your NRZ signals and your coherent signals, you reduce the impact that you see here. Self-phase modulation is what happens when the change between a 1 and a 0, if you're making the light really bright or really dim back and forth, the change between a 1 and a 0 can be so bright that it actually causes the Kerr effect. It actually causes the amount of power in the system, changes the index of refraction and causes light to be steered. So you can actually have things where it actually causes the light to be constrained inside of the fiber much tighter than it wants to be. There's all kinds of different weird effects that start to happen when you start to put really high power systems out there. But remember, all of this is tied to energy density. It's about what happens when you put a lot of power into this little tiny fiber. So there's a concept in fiber called the effective area. It's the size of the glass that is actually carrying the wave. So like I said, chromatic dispersion helps this because it's causing a walk-off. It's actually causing the power to be carried at a different moment in time through a different piece of glass. If you have a large effective area fiber, if you have a wider core of fiber, that works also. But to a certain point, right? If you go too big, then you cross into multimode and you're suddenly not doing anything useful long haul. So this is called the fiber's effective area. And if you can't find the effective area, you can go find the mode field diameter and do pi r squared. This is telling you how large the core is, how much of the core there is to carry the fiber. And so submarine cable tends to be the largest. So a submarine cable like a Corning Vascade can be 150 micron core. The bigger the core, the more power you put in. So you're able to put in brighter signal, you're able to carry that further. You care about that when you're doing these many 1,000-kilometer submarine spans. One of the trade-offs with this is the larger the effective area, the less Raman gain you have, because Raman gain is a kind of nonlinear effect. So it tends to be pretty proportional, right? So if you have a smaller effective area fiber, then your Raman works really well, and you use Raman amplification. And if you have this big fiber that's designed to take a lot of power, then you don't need as much Raman amplification, and you get it back, and you can put more power into it in a straight EDFA. So it depends on the kind of fiber that you want, but you can go either direction and still get very similar outcomes. So now I'm going to talk a little bit about what we actually transmit over the fiber itself. So modulation. Remember, at the end of the day, we live in an analog world, right? We think we're sending ones and zeros, but we're not. We're sending waves. So we have to figure out how do we actually encode our digital signals in these analog waves. And light is just another kind of electromagnetic wave, just like everything else. So the simplest form of modulation, the one that you'll see in the most basic kind of optics, is something called IMDD. And that stands for intensity modulation with direct detection. The most common form of that specifically is something called NRZ, which is non-return to zero. You'll also hear this called amplitude shift keying, which is just like AM radio, which is all just a really fancy way of saying bright for a 1 and dim for a 0. That's all this is. And so a direct detect system means you have a photodiode, and it looks at this light, and it sees bright, dim, bright, dim, bright, dim, and it turns it into 1s and 0s. So historically, most of our fiber systems have been built purely around NRZ. All of your 10 gig signals and below are very much in this category. Most of your client optics are in this category. And only the newest, highest end long haul or high capacity systems are something else. So baud is what happens when you have a signal state. So it's the rate at which you modulate a signal. So if you send a 10 gigabit per second signal, that means you flash between a bright or a dim 10 billion times a second. That's 10 gigabaud. You carry 1 bit per baud, and so there's your 10 gigabit. That's your data rate. So this worked really well up until about the 10 gigabaud range. And as you start to go past 10 gigabaud, then it starts to get very, very difficult to deal with dispersion. So the dispersion impacts you, chromatic dispersion impacts you as the square. So as the gigabaud rate goes up, it harder and harder and harder. So what happens when you can't increase the gigabaud rate anymore? What happens when you need to encode more data and you don't know how? Well, so there's a couple things that you can do, right? One is you can add more states to the amplitude modulation. So instead of having a bright and a dim, you could have a bright and a really bright. So instead of 2 states, you might have 4 states. The other way is something called phase shift keying. So that's a way to modulate data based on another property of an analog wave called the phase. So in phase shift keying, what happens is you think of a sine wave, right? Here's a wave. It's doing this. If you want to modulate on phase, what happens is you have a sender and a receiver, and they both agree on a specific frequency. So they say, we're going to use 196 terahertz. This is our frequency. I am going to listen to it. You're going to send it. And you actually have a laser on the receive side. So just as the transmitter has a transmitting laser, you have a laser on the receive side, and you dial it to exactly the same thing that the transmitter is going to be sending. And so then you're able to modulate by offsetting the phase. Instead of making it brighter or dimmer, you shift the point where does it go to zero? Where's the peak of the wave? Where's the zero of the wave? Where's the low peak of the wave? You move that back and forth. That's the phase. And by comparing the local oscillator, what the receiver has and what it knows is that laser versus what the transmitter's sending, you can encode data. That's phase shift keying. So that introduces a class of optical called coherent. So this is where we started to introduce phase shift keying as a way to encode this data. And it's named after the ability to track phase changes in optical signals. That's called phase coherence. So coherent is kind of a marketing name for the general class of technology. And it provides a new way to modulate signals. So it's not just bright dim, bright dim. So like I said, there's a local oscillator. There's a laser on the receive side that you dial to exactly what you want. And you compare the difference. You modulate on phase. And you're able to encode data in a completely different way. But that's not as easy as it sounds. Like that's way more complex than a simple photodiode where you just look at a light and see bright dim, and turn it into ones and zeros. So to decode this, you need what's called a DSP, a digital signal processor. And this is a highly advanced chip that is purpose-built to decode these analog signals and figure out what you were trying to encode. So it starts to have the complexity, not quite of like a modern CPU, but it's up there. It's a very, very advanced, very purpose-built, specific processor for decoding these signals. And there's many different manufacturers of these, and they treat them as closely guarded secrets with lots of research that goes into the technology that's behind these. And these DSPs are what's able to decode this signal and tie it all back together. So when we introduced coherent, we had an immediate overnight jump. We went from, we were doing 160 channels of 10 gig and hitting all of these NRZ limitations to, we moved immediately to 96 channels of 100 gig. So we jumped overnight from 1.6 terabit to 9.6 terabit. It gave us our first true 100 gig optical signals. So instead of just N by 10, we had real native 100 gig, and then it went up from there. Coherent also greatly eliminates the need for dispersion compensation. So the DSPs actually like dispersion. It helps them calculate the signal better. It's better to have dispersion than to have no dispersion, and they can eat tremendous amounts of it. So you're no longer having to do all this dispersion compensation every hop, and it greatly enhanced our bandwidth. So where do you go from there? Well, now that we're modulating on phase, you add amplitude back into it. So you have something called QAM, quadrature amplitude modulation. So it's basically just a combination of phase shift keying and amplitude modulation. So now you have two different modulated carriers that you can send at the same time, the same frequency, but with a phase offset. And you're using a DSP to computationally recover from that. And as you get more and more and more complex, you create more potential states where you can encode data. So we have 8 QAM, 16 QAM, 32 QAM, 64 QAM. You move up the scale in different potential states. And now we even have irregular constellations. We have these half QAM states where some of the time we're using more states and some of the time we're using less. There's a lot of fancy technology that's out there to encode more bits per symbol rate. So you get 4, 5, 6 bits per change of baud per symbol. We also use polarization multiplexing. So remember that light, among the many things that we don't really understand about it, is just a wave. It's a wave propagating through space. And because we live in a three-dimensional space, we have an X and a Y axis. And light you can send a horizontal wave propagating like this, and you can send a vertical propagating wave like this. And as long as they're completely horizontal, completely orthogonal to each other, they will propagate without interference. So you can basically double the amount of capacity that you can send through a three-dimensional fiber by sending these two polarizations of light. And the DSPs decode all of this in the end and computationally recover what it was you were trying to put in there. So what you end up with is you look at the bit rate being a multiplication of your polarizations, or number of carriers, times your baud rate times your modulation. So today we only have dual polarization. There's other things that we're trying to figure out how to do this on, like orbital angular momentum and things like that. But today we just have polarization, so we get two carriers. We have a baud rate. So the baud rate, the higher the baud rate, the wider the channel size you need, because I said the baud rate is directly proportional to the width of the laser. So you need these better quality DACs, but we get better and better and better at designing better DACs that are able to work with these higher baud rates. And modulation is how we encode the data. So the higher the modulation you go, the higher an OSNR you need. So you end up with this big table, right? You end up with these many different ways to achieve. So let's say, for example, you wanted to achieve a 100 gig data rate. Well, what that might look like is a 32 gigabaud signal with two polarities encoded at QPSK, so DP, dual polarity QPSK. So that's just straight phase shift key. So that signal ends up fitting inside of a 37.5 gigahertz channel. And by the time you add FEC overhead, it needs 128 gigs of data to carry your 100 gigs. And it lets you work at these very low OSNRs. So you could get down to like an OSNR of 10 dB, which is extremely low. And those are the kind of signals that you can carry tens of thousands of kilometers across all the way around the world and still be fine. But if you want to carry a modern higher end signal, say you want to carry a 600 gig wave, you would do that with a potentially 64 gigabaud signal done at 64 QAM, and it needs this wider channel and it needs a much higher OSNR. But you get to pick and choose. You get to decide which given the properties of your line system, which level of signal you want to carry. So here's an example of a modern DSP and what that looks like. So Acacia is one of the leading manufacturers. They're kind of like the Broadcom of the optical DSP world. Most people use them. So this is the latest product that they ship, and here's all the different combinations. Here's all the different ways that you can achieve different bit rates. So if you want a 200 gig signal, you might do it at 34 gigabaud at 16 QAM. You might do it at 46 gigabaud at 8 QAM. You might do it at QPSK at 69 gigabaud. And each one has a performance trade-off. So here's what I mean by that. Let's consider two different ways that you could get to 200 gig, right? So one was we do it with two polarities, 32 gigabaud and 16 QAM. So that requires a 19.5 dB OSNR, which is healthy. But it fits into a very small channel. It fits into a 37.5 gigahertz channel. Another way that you could get 200 gig, instead of trying to up your modulation, is up your baud rate. So instead do 64 gigabaud, but do it at QPSK. Same data rate, same 200 gig, but now we can go way down to a 14.5 dB OSNR. So the benefit there, we can carry that potentially thousands of kilometers longer, but what we've traded is we now need a wider channel to do so. So remember, as the baud rate increases, the channel size increases proportionally. So the more spectrum you can allocate to a particular carrier, the more efficient you can be with it, the more you're able to do this. The downside there is if you're running a brownfield network, so let's say you've got a whole bunch of deployed Rotoms out there and they only pass 50 gigahertz. So a 50 gigahertz Rotom might only have a 37.5 gigahertz passband. You're only able to do the 32 gigabaud signal. You're not able to do a 64 gigabaud signal. So the wider your channels are, or the more modern your system is, and the more that it's able to work with FlexGrid, the more efficient you're able to get with your carriers. So some more things about coherent. Like I said, it eats dispersion for lunch. So you can easily do hundreds of thousands of picoseconds per nanometer. And in fact, coherent systems work better with dispersion. Coherent can lock on because there's a local oscillator, because you're doing phase shifting, you're able to lock on to a specific frequency. So in a lot of cases, you don't need a mux. That's how a CDC Rotom works. You're not actually filtering out, well, channel 1 went here and channel 2 went here. You're sending both signals to both ports, and you're letting the receiver lock onto only what it cares about and discard the rest. But there's a lot of downsides, right? These are very expensive, power-hungry components. They're extremely difficult to integrate into pluggables. So pretty much a rule of thumb is whatever we consider the pluggable that we use for our high density, 100 gig client optics is always going to be too small for whatever the latest, greatest generation of DSPs are that can live outside in a completely different thermal envelope. And as we increase those pluggables and as those pluggables change, the DSP technology changes too, and it parallels each other quite well. So it's very, very difficult to get coherent shoved all the way down into a pluggable. And by the time we do, we'll probably have decided we don't like that pluggable format anymore and we'll have wanted to switch. So the other way that you could do this, remember when I said you can have multiple states. You can also have, so NRZ is what's called PAM2, pulse amplitude modulation with 2 states, so bright dim. Another way to increase capacity is to add more states. So there's a technique called PAM4. So now we have a bright and a really bright, a dim and a really dim. So you're able to encode 4 potential states, right? So you end up with this thing that looks like this. So as you move from one state to another, you're able to encode whether it was a 1-1 or a 1-0, things like that. So there's a lot of work that goes into, on this specifically, a lot of the 400 gig client optics that we're using are all going to be based around PAM4 technology because it's very, very difficult to do 100 gig NRZ single lambda. And so like if you consider the cheapest 100 gig is 4x25, how do you do 4x100? That's still 100. You need a 100 native optical carrier. A lot of the 400 gig things are built around doing 50 gigabaud PAM4 and multiple channels of that. So PAM4 is very much tied to everything that we're doing in 400 gig client. And it's used in things like DWDM tuned QSFP 28s done in PAM4 that you can carry over distance. There's a new technology that people are very excited about called 400 gig ZR. So this is an attempt to get coherent technology down into a pluggable. So I have to tell you right now, this is still very much in the R&D phase. None of this exists outside of the lab. The standards are still being developed. It's still a work in progress. So why would we want to do this? Well, there's a lot of overhead you can potentially take out if you can eliminate external transponders. So consider if all you're doing with your optical network is lighting, you run this big optical network and you create packets and then you go right into a router. You light the optical network with your router. If you aren't selling an optical wavelength, if you aren't doing anything, if all you're doing is lighting your packet network, you could have been a lot more efficient if you had put that directly in the router. If you could bypass those client optics, you're saving yourself potentially some SR4 optics or some LR4 optics and some patch cables. You're simplifying your management. You now don't have a second external transponder to manage. So the way that this is talked about is what's called IP over DWDM. It's just straight putting the DWDM directly into the router. And this is something that the industry has gone back and forth on for many, many years. Some days it's the latest fad, some days if people are moving away from it. There's advantages and disadvantages to each. Potentially you can eliminate all of that. Router vendors have been doing have been building coherent line cards recently. So they've been taking what would have been a DSP, an external DSP, and just putting it on the line card. So it's still functionally the same thing, but it's now on the router instead of requiring an external transponder. The problem with this is the rate of evolution, the rate at which the DSPs change is a bit different than the rate at which the switch boards change. So largely what you end up doing is creating a crippled line card that now has a lot less capacity for a lot more money when you would have been a lot better off just running an SR4 optic and a patch cable. So 400 gig ZR is an attempt to actually do this and get it down into a pluggable. So it'll be a 400 gig, so think a QSFP 56DD that'll actually be able to do coherent 80 kilometer DWDM into a pluggable. It's very, very complex. It's still a very difficult engineering challenge. We're a long ways away from that being ready. And like I said, there's a PAM4 DWDM also. You'll see commercial systems like EDFEH makes the most prevalent one of these systems, where you take two 56 gigabaud or 56 gig systems. So it's 28 gigabaud at PAM4. Two carriers offset at plus and minus 25 gigahertz. So you're able to pack a 100 gig DWDM channel into a QSFP 28, put it directly into your device, and you can do 80 to 120 kilometers. But there's a lot of caveats attached to this. So you need special flat top muxes. So if you have standard off the shelf muxes that you've always worked with, that have always been fine till now, well, they're not going to work anymore. They're not going to carry the spectral width that you need for this particular signal. They're also not going to work for your 600 gig coherent systems either. So a lot of folks are going to need to go out and upgrade. With PAM4 specifically, you have very, very tight dispersion compensation tolerances. So you have to get to within plus or minus 100 picoseconds per nanometer, which is very, very, very tight. You have to amplify straight out of the card. So you can't even take one optic and link it directly to another optic sitting right next to each other. You have to have an amplification pass just to ever be able to link once. And by the way, 400 gig ZR is going to be the exact same way. So it's not going to be this panacea of, oh, it's just like old tunable DWDM where I plugged it in and it worked and I didn't need amplification or to know anything optically. You actually will need to run real line systems and amplification no matter what you do. And these things have a very high OSNR requirement. So basically you're never able to pass a PAM4 system through a Rotom. The impact from all the amplification is way too much. So now I'm going to talk a little bit about engineering that you can do. Insertion loss. Even the best connectors and splices aren't perfect. So every time you connect two fibers together in any way, shape, or form, you're going to get loss. So a typical budgetary figure will be 0.5 dB per connector, but the actual number will vary depending on the conditions, how clean the fiber is, what the mating type connector is. Insertion loss is also used to describe loss from a mux. So it's just the penalty you pay from plugging in the fiber. So you might plug into a 40 channel DWDM system and you might have a 3.5 dB loss just from going into that mux. You might plug into an 80 channel system and you might see a 9.5 dB. Remember, an 80 channel system is really just two 40 channel systems glued together with an interleaver. That's why that insertion loss is so high. That's why you typically see these systems only used on high-end amplified systems where you can overcome that kind of loss. When you plan an optical network, you need a budget. So when an optic says 10 kilometers, that's the loosest of guidelines. I've seen optics that say 10 kilometers that I can take 30 kilometers. I've seen optics that say 1 kilometer that I can take 25 kilometers. It absolutely, positively is just a bare guideline. So you need to actually look at the light levels and what impairments you're going to hit as you go across the signal. But you want to leave some margin. You want to leave some room so that as the transmitters might cool with age, so 5 years from now you don't find that you've crossed this magic threshold and that your signal goes down. And remember, you have to leave room. Like what happens if there's a fiber cut and the splice crew goes out and they fix it, but they don't fix it quite perfectly and there's a little bit more loss, or just technicians going out in the field and bending the fiber cables. You have to leave a little bit of margin in there. I talked about this a little bit earlier, but different connector types. So primarily, you'll see these called PC or UPC, which people think they stand for polished connector. They actually don't. They stand for physical contact. So your blue fiber ends are your PC or UPC. Your green fiber connectors are your angled physical contacts. You see they have a cut that's at a slight angle. It's an 8-degree angle. The reason for this has 100% to do with reflections. It doesn't make the signal carry any better in any way other than reflections. In a regular UPC system, when you unplug that fiber cable and there's nothing plugged into the end of it, it now starts to transmit a lot of that light back. So if you have a very high power system, you can transmit more power back and you can actually cause damage and do things that you don't want to do. And an APC system, because you have this little 8-degree cut, when you unplug that fiber cable, it's now transmitting the power into nothing. It's going into the cladding and dissipating. So you see this used whenever you have a high power system of some form. That's the only time that it matters. When you amplify, when you work with a signal, you have to do what's called the 3 Rs, 1R, 2R, and 3R. So 1R is amplification. So when you go through an EDFEH and you make it brighter, you've just amplified it. You haven't reshaped it, you haven't looked at the signal in any way. You can do reshaping, you can restore the ones and the zeros, but you don't always have to go all the way to retiming. So retiming is a full OEO. You've completely decoded the signal, you know exactly what it was originally, and now you re-encode it going forward. So that's typically what happens in a full transponder. Bit error rates, as you start to cause impairments, typically links don't just go out and die. You don't just cross this magic line where all of a sudden it's either working or not working. What tends to happen is as it gets worse and worse and worse, the bit error rate goes up. The potential that there's an error goes up. So when you talk about testing a span, you talk about testing a link, you have to put a certain amount of data across it to have a certain level of confidence that a link will work. So for example, if you want to be 99% confident that a 100 gig link has a 10 to the 13 bit error rate, you have to generate 100 gig traffic for 3 hours and 29 minutes, right? After you've done 3 hours and 29 minutes of traffic and you've seen no loss, then you have a 99% confidence this is the bit error rate. That's why when you turn up telco circuits, if you ever see people come out and leave test sets running for a really, really long time, that's what they're trying to certify is this is the certain bit error rate. And the lower the speed the link, the longer you have to leave that test running. I'm going to skip some stuff for time. Optical power meters, light meters. Tools of the trade, simplest thing on the planet, you go out there and plug your fiber into it, look at it, and it tells you how bright the signal is. And it's going to display the values as either dBms or milliwatts. If you have a light meter and it has a relative loss mode, if it has a button that says dB, that is meant to be used as part of fiber testing. So that's meant to be used with a known light source on the other side so that you can compare how much loss you have and say, hey, this cable has this much loss. But when you're actually plugging into a router and wanting to see how much light am I putting out, you need to be in dBm mode. You need to be in the absolute mode. So remember, if I had a nickel for every time someone told me they just measured plus 70 on my fiber, I'd be a rich man. OTDRs, an optical time domain reflectometer. So this is a tool that helps you characterize fiber. What it does is it sends pulses of light out into the glass and it looks at the reflections. And by sending these really bright pulses of light and waiting and seeing exactly how they come back and varying them over time, you can measure, you can find the splice points. You can see what's the rate of loss over distance, where are the splice points, are there any potential issues, are there core mismatches. It helps you characterize the fiber. So you typically use that when you're provisioning a new fiber or troubleshooting it in some way, trying to figure out where the cut is. It'll tell you 27 kilometers down this span is where the issue is. Here's an example of what that output looks like. People ask me a question, can I really blind myself by looking into the fiber, otherwise known as beware of big scary lasers, do not look into beam with remaining eye. I put these stickers out on patch panels randomly sometimes just to mess with people. It's funny. So laser safety, lasers are grouped into 4 main classes for safety. So class 1 is completely harmless and normal use. It's either so low powered that it could do nothing to you, or it's completely inaccessible during normal operations. And class 1M is harmless as long as you don't look at it in a microscope. Class 2 is harmful only if you intentionally stare at it. So like your supermarket scanners. If you really wanted to, you could hold your eye open and do this, but if you don't want to blind yourself, don't do that. Class 3 is something that can be harmful if you look at it accidentally. So there's 2 different ways that that's split. There's an old system and a new system. It used to be called 3R and 3B. Now it's called, or it used to be called 3A and 3B. Now it's called 3R and 3B. And that has to do with different frequencies of light and different power levels will be given different classifications depending on how likely it is to cause harm. So like those super high-powered laser pointers people buy on the internet, I call them the Department of Homeland Security bat signals. Those a lot of times are into the 3Bs or even class 4. And class 4 is something that burns, melts, or destroys Alderon. It's the industrial lasers that are very, very powerful that would actually cause like thermal damage. So when you look at lasers from a networking perspective, it's classified, these are all infrared. These are all infrared lights. So infrared can be broken down into 2 classes. So it's called IRA and IRB. So IRA is near infrared. It's very close to the frequencies of light that we see. And IRB is far infrared, shortwave infrared. And that's so far away that we can't see it. So laser safety is actually based on what can enter the eye, not just the absolute power level. So the cornea actually does a really good job of filtering out light that the eye, if you can't see it, what's the value in it coming through your cornea? So IRB, the far infrared, actually does a really good job of getting filtered by your eye. It's the light that's much closer, the lower frequencies that are closer to the visible light that we normally look at that get through. So these are the power requirements for these are the continuous no auto shut-off power requirements for different class lasers. So if you wanted to send an IRB signal over 27 dBm, you'd be into a class 4 laser territory. You need these active disconnect features, all kinds of laser safety things because you could potentially hurt yourself. So as far as this goes in the field, routers, essentially there's nothing that you will find on a router that is anything other than a class 1 laser. Even your long reach, 80 kilometer, 200 kilometer, it doesn't matter. What's happening is you're not making the lasers transmitting any stronger, you're making the receiver more sensitive. So the laser power is pretty well fixed. The only time you really get into something that's potentially harmful is when you have amplifiers. So you now move into 3R or 3B. Systems. If you have Raman amplification, that's pretty much always a class 4. Raman amps are very, very high end. And these typically have some kind of an auto power reduction or shut off or break. I'm going to have to, whatever. If you have a lot of DWDM equipment, if you have like 40 channels that are all muxed into one, well, now you've just made the signal 40 times brighter. So potentially you could take something that was completely harmless, but now you have 40 of them. You could look at it and hurt yourself. So should I be wearing safety goggles in the colo? Generally speaking, no. Your client optics, like I said, are all class 1. Almost everything that you'll touch on a router is class 1. Even your amplified DWDM systems, unless you're looking at it with a fiber microscope, you're probably fine. Like it tends to spread out pretty quickly. Why even look at the fiber anyways? You're not actually able to see infrared on any signal, but you're able to see the sidebands. So if you look at like an 850 signal, you'll see a little bit of red, but you're just seeing the imperfections of the signal. I'm going to skip a bunch of stuff for time. Do I actually need to be concerned about bend radius? Yes, it's a real issue. You can actually cause light to leak out the side. So here's an example of what happens when you take a bright LED and bend the fiber past its bend radius, and it literally causes it to leak out the sides of the fiber. So you really want to use bend insensitive fiber if possible when working in a data center so that you don't accidentally cause issues. Different wavelengths can talk to each other. I've said all this before. Do I really need to clean the fiber? Yes, you do. Yes, so what a lot of people don't understand, you've got a mating force of 2.2 pounds over a 200 micron surface area. That's 45,000 pounds per square inch of pressure coming together in these very, very small surfaces. So if you have a piece of dust in there, it can permanently pit the fiber. It can ruin that fiber in ways that you might not know until you're way, way, way further down the road and causing problems. So when in doubt, buy a really cheap cleaning kit. They're all over the place. Other miscellaneous fiber information. If you've ever wondered how fast light travels through fiber, the speed of light is here. SMF28 has a refractive index of 1.4679. So that means light travels through fiber at 204,000, blah, 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 blah. So if you turn that into time, for every 1 millisecond, for every 100 kilometer of fiber, or 62.5 miles of fiber round trip, you see 1 millisecond of latency added to your fiber. So if you ever wonder why you see much higher values than that in real life, remember the fiber's rarely laid in a straight line. It's usually in rings, going through structured cabling all over the place. There might be dispersion compensation spools, but that's how fiber actually creates latency, actually affects latency, and causes that as you go thousands of kilometers and show. That's pretty much it. Questions? Questions? No? And in that case, enjoy your beer and gear.